Okay, in this video we're going to finish going through the multiple choice questions from practice exam 3, so questions 16 through 23. So questions 16 and 17 both refer to this scenario right here. It says scientists studied how much time students spend on a particular college entrance exam. The mean time a student spends on taking a college entrance exam is 64 minutes, and the standard deviation is 11 minutes. So question 16 is asking you to interpret the value of the mean, and then question 17 is asking us to interpret the value of the standard deviation. So starting with 16, they're asking us to interpret the value of the mean, which is a measure of center. So we want to pay close attention to how the sentences are worded. A lot of times it's just the difference of a couple different words that change the meaning of the answer choice. So first answer choice A, all students spend about 64 minutes taking the college entrance exam. Okay, so that seems reasonable. They tell us the mean time is 64 minutes, and this choice is saying all students spend about 64 minutes taking the college entrance exam. One thing you always want to watch out for is when they're using the word all. They're saying all or every single student spent about 64 minutes. And that's not what the mean is telling us. So the mean is telling us that 64 was the average. We could have a bunch of students who spent only 5 minutes and a bunch of students who spent 3 hours, and we could calculate the mean and it could still come out to 64 minutes. But it doesn't mean that all students spent about 64 minutes. B, half of the students spend more than 64 minutes and half spend less than 64 minutes taking the college entrance exam. So that also seems reasonable at face value. But what they're actually describing here would be the median. So the median is that exact middle value where 50% of the values will fall below it and 50% above it. And that's not necessarily the case with the mean. Answer choice C, the typical time students spend taking the college entrance exam is 64 minutes. So C would be the correct answer. It's very similar to A, but again, that word all makes a huge difference in the meaning. 17, they're asking us to interpret the standard deviation. So standard deviation, that's talking about the spread of the data values. Are they similar in group closely together, or are they spread out and far apart? A says a student will spend 64 minutes plus or minus 11 minutes taking the college entrance exam. So that doesn't seem particularly unreasonable, but again, it's sort of the idea of the absolute. it's saying a student will spend 64 minutes plus or minus 11. And we don't know that to be the case. There's going to be some variation, obviously, in the amount of time students spent taking the exam. So I can't say for a fact a student's going to spend 64 minutes plus or minus 11 minutes. B, the typical variation from an individual, and these are worded in somewhat of a confusing manner, these answer choices. I had to reread them a couple times myself. I thought it was a typo at first. So B, it says the typical variation from an individual student's time spent taking the college entrance exam, and the mean is 11 minutes. So here, what they're saying, the typical variation from some individual student, how long they took taking the exam, and the mean value, mu. They're saying the distance between these two is equal to 11 minutes. And they use the word typical variation, which is a good thing to see that typical. It's not an absolute. It's not saying all students have a difference of 11 minutes between the mean time and their time. C says the distance from the mean time spent taking the college entrance exam and each student's time is 11 minutes. So again, that seems reasonable. They sort of have the right concept, but it comes down to that absolute again. They're saying the distance from the mean time and each student's time is 11. So it's not going to be the same case for every student. All students are going to take a different amount of time testing, so this cannot be true. D, this is the distance from an individual student's time spent taking the college entrance exam, and the mean is 11 minutes. So similar to what they're describing in B, they're saying the distance between an individual student's time taking the entrance exam and the mean value is 11 minutes. So B and D are pretty similar, so I sort of want to dig deeper a little bit and look for any clues I can find in the wording that might help me eliminate one of them. B, it's saying the typical variation. So typical means that happens often, but not necessarily all the time. D is the distance from an individual student's time spent taking the college entrance exam, and the mean is 11 minutes. So right there when they're saying is 11 minutes, they're implying that's going to be the same for all students, which is not the case. So B would be the correct answer. And you can notice with both 16 and 17 describing the mean and the standard deviation, both of them are using that word typical. They're not saying a student's value will be this or all students will have this value, but the typical. Okay. So next page, we just have one question on it, question 18. And question 18 says, which one of the following normal distribution plots has a mean equal to 100 and standard deviation equal to 15? So below we have 4 different normal curves we're looking at. The bell-shaped curve. So the shape of each graph is the same. What does differ are the values on the bottom of the graph. So what we want to remember for a normal distribution is that the mean value, oops, sorry, you can't see that, is always going to be exactly in the center of the distribution. And the standard deviation, that's telling us how much space there's going to be between the mean and the next value they have listed, the next hash mark. A lot of times these distributions will show the mean and 3 standard deviations. So you'll have that one hash mark in the middle representing the mean. And then as we move out from the mean, we'll have 1 standard deviation, 2 standard deviations, 3 standard deviations. So first thing we can check on is the mean. They said it's equal to 100. So that value in the exact middle needs to be 100. So distribution number 1 looks like we have 100 exactly in the middle. So that's good. I'll take a look at number 2. If I find the mean or the middle value, here it's actually 15. So I can go ahead and eliminate number 2. Distribution number 3. If I look at the exact middle value, it is 100. So we can keep 3. And distribution number 4, if I look for that exact middle value, here it says 100.0. So even though it's written slightly different, I still have my center value being labeled as 100. So I can keep distribution 4. So 1, 3, and 4 are all accurate when it comes to the mean. So the other thing we need to check out is the standard deviation. They said the standard deviation is 15. So that's telling us if we have a mean value in the center of 100, each hash mark I move to the right of 100, I should be increasing by 15 each time. And as I move to the left, I should be decreasing by 15 each time. So that means if 100's the center and the next value to the right has to increase by 15, that means that next value we see should be 115. And the next hash mark, we'd have another standard deviation. So it's going to go up 15 again, so 130. And a third standard deviation would be 145. As we move to the left from the center, this is staying, each standard deviation is going to go down by 15. So if I subtract 15 from 100, that means the next number to the left of 100 should be 85. And if I go at a second standard deviation, I'll take away another 15, so this value should be 70. And third standard deviation to the left, if I subtract 15 again, would be 55. Sort of messy, but that is the pattern of numbers we want to look for in the distributions. So if we take a look at number 1, again we have this mean in the middle, 100. If I move one standard deviation to the right, it shows a value of 115, which is good. That's what we said it should be. And if I go over a second standard deviation, I have 130, and a third standard deviation, 145. If I go back to the center and look at the standard deviation values to the left, it should be going down by 15 each standard deviation, and it is. So number 1 looks pretty good right now. So I'll take a look at 3. So 3, we had 100 here in the middle, which was good. If I look at the next number over, it's 105. So I can eliminate option 3. Here I'm only going up by 5 each tick mark or hash mark. So that means this would be describing a situation where you had a mean of 100 and a standard deviation of 5. So last, number 4, I have 100 in the middle still, even though it's written as 100.0. If I move to the right one standard deviation, I see 102.5. If that's not correct, I can eliminate number 4. So distribution number 4 would be describing a situation where you have a mean of 100 and a standard deviation of 2.5. So the correct answer for 18 would be distribution number 1, answer choice A. Okay, next question, number 19. Says, for the data displayed in the histogram below, would it be reasonable to use a normal distribution as a model for the population represented by this data? So we have 5 different answer choices, all of them saying either yes or no, and then providing their reasoning. So let's go back to the question and see what they're asking. Asking if it's reasonable that we could use a normal distribution to model this. So we want to think of what that means, what a normal distribution would mean. So to qualify as a normal distribution, the distribution must be symmetrical, approximately symmetrical. It may not always be exact, but overall it should be symmetrical. You should be able to fold it in half, and each side would be a mirror image of the other side. It should be bell-shaped, so it should start almost on the x-axis, go up and come back down to the x-axis. Other thing we know about a normal distribution, since it is symmetrical, that tells us that the mean and the median should have the same value. They're equal to each other. Whereas if the distribution was skewed to the left or to the right, the mean and median would not be equal to one another. So if we look at the overall shape, it sort of looks like maybe it could be bell-shaped. I see it starts sort of low, goes up, comes back down again. So one thing I can do to help make my decision is sort of draw in a curve and take a look at what it looks like. So I'm just going to go down and cross the outside corner of each bar. So it sort of looks like bell-shaped in that it goes up and comes back down. However, this is not symmetrical. If we had to describe this, we have the different options. It could be symmetrical. It could be skewed to the left. Could be skewed to the right. Or it could be uniform, where all the bars are the same height. So these are our different descriptors for the overall shape. Here is my tallest bar right here. And one thing I can look at is if I go to the left, I only have 2 bars. Whereas if I move to the right, I have 1, 2, 3, 4, 5, 6 bars. So 3 times the number of bars. They don't have to be exactly equal, but what this is telling us is this distribution is skewed to the right. The mean is being pulled to the right, so in this case the mean would be greater than the median. So for our answer choices, we've decided no, this wouldn't be reasonable to use a normal distribution for. So that leaves us looking at answer choices C, D, and E. They're all no's. So we'll take a look at the reasoning. C, no, because the histogram does not have enough observations. The number of observations in this case isn't going to matter. Looks like we have plenty of observations. If you think the vertical axis here is frequency, we have plenty of observations. That shouldn't be a problem. So D and E are similar. D is saying no because the histogram is skewed left, and E, no, because the histogram is skewed right. And again, the shape of this, it is skewed to the right, are being pulled to the right. So the correct choice is E. Number 20. In a large study on male health, scientists studied the heart weights in ounces of adult males. Below is a probability distribution for the weights of adult male hearts. What does the shaded area represent? So if we take a look here, this looks like a normal curve, and they're telling us it's a probability distribution. So this is representing the weight of male hearts in ounces. So my middle value here, 11. So I could say the mean weight of an adult male heart is 11 ounces. I could also determine the standard deviation as well if I wanted. So from the center 11, if I move to the right, I have 13, the value went up by 2. If I moved to the left 1 deviation, I have a 9, it went down by 2. So this tells me that the standard deviation is 2. So, other thing we want to look at, they're ultimately asking us, what does the shaded area represent on the right? One thing I am going to want to know is I sort of want to estimate what value this would be equivalent to. So we can see it looks like it's pretty close to halfway between 13 and 14. So the shaded area is most likely starting at 14, and then everything to the right is shaded. So a couple things to keep in mind with normal curves and probability distributions. The space under the curve is representing area. So areas under normal curves represent probabilities. So particular areas tell us a probability or how likely something is to occur. Another characteristic to keep in mind is that the total area under the curve is always going to be equal to 1. And that sort of makes sense. We're saying this, the area corresponds to various probabilities. If you remember, probability is always a value from 0 to 1. Another detail to think about, they're talking about area here. What does the shaded area represent? So when we're talking about area, we're talking about something that's two-dimensional. It has a length and a width, or a base and a height. So that limits our interpretation. And you'll see what I mean by that as we look through the answer choices. So, answer choice A, says the probability that an adult male heart weighs more than 13 ounces. So this answer choice is saying that's what the shaded area represents, the probability that the adult male heart weighs more than 13 ounces. That's not accurate. If this was the case, more than 13 ounces, that means 13 is where our shaded area would have started, but we've already decided it starts at 14. So I can eliminate choice A. B says the shaded area represents the probability that an adult male heart weighs 14 ounces. So that is implying that it's exactly 14. Not more than, not less than, but exactly 14. So on the normal distribution, we know that the shaded area starts at 14, but it continues to the right. It could not be exactly 14 because 14 is just a straight line. And a straight line is only one-dimensional. And here we're talking about area, two-dimensional. Has to have some space. So it's not ever going to represent the probability of an exact value. So last two options, C and D, they're pretty similar. So they're saying that the shaded area represents the probability that an adult male heart weighs, and then we're choosing from either more than 14 ounces or less than 14 ounces. So in this case, we know our shaded area starts at 14. And then everything to the right of 14 is shaded. And you can sort of look at the numbers. We're shading area where the numbers are getting bigger and bigger and bigger. So that tells us that this is depicting the probability of an adult male heart weighing more than 14 ounces. So the correct answer choice would be C. So you could find the exact area of this shaded space. Let's say it ended up being 0.21. That's the area of that space. Remember, the total area under the curve equals 1. So if the entire curve was shaded, it would have a probability of 1. The event would be certain. So our area that's shaded is going to be somewhere between 0 and 1. If I had to estimate, I'd say maybe that represents an area of 0.21. And we have ways to calculate that. If that was the case, the area was equal to that value, 0.21. What that means, what that's telling us is that 21% of adult male hearts weigh more than 14 ounces. That's what that would really be telling us in the context of this problem. Okay. 21. Scientists did a study on adult male noses. The scientists measured how far a man's nose sticks out from his face. The distribution of these measurements is normal, with a mean of 2.6 centimeters. The probability that a man's nose sticks out more than 2.8 centimeters is 0.03. If you look at 500 men, how many would you expect to have a nose that sticks out more than 2.8 centimeters? So before we get to the 500 men, we want to determine what proportion of men have noses that stick out more than 2.8 centimeters. And luckily they have given us that information in the problem. So here when it says the probability that a man's nose sticks out more than 2.8 centimeters is 0.03. They're saying 0.03 is the probability of this happening. This would also be equal to 3%. So this is saying the probability that a man's nose sticks out more than 2.8 centimeters is approximately 3%. So that's the overall proportion. So now they're saying we're going to be looking at 500 random men, and based on this information we have to decide how many of those 500 men would we expect to have a nose that sticks out more than 2.8 centimeters. So we've already decided the probability of that happening is 3%. So really what we need to do is figure out what is 3% of these 500 men. So again, to make this calculation, I just want to change my percent to its decimal form, 0.03. And then I multiply by the total amount, which was 500. And that would equal 15. So 21, correct answer choice is A, 15. So if we had a group of 500 men, we could expect about 15 of them to have noses that stick out more than 2.8 centimeters. 22. So it says the distribution of heights of adult men is approximately normal. The distribution has a mean of 69 inches and a standard deviation of 2 inches. Bob's height has a z-score of negative 0.5 when compared to all adult men. Which of the following statements is true? So before we get into evaluating which statements are true, I sort of want to help us visualize what this information is telling us. So we know that the distribution of heights is normally distributed. So it can be represented by a normal curve or bell curve. And they told us the mean was 69 inches. So that means our exact middle value here would be 69. They also tell us the standard deviation. So it says the standard deviation is 2 inches. So if I move 1 standard deviation to the right, the value is going to go up by 2 inches. So 1 standard deviation above the mean would be 71. 2 standard deviations above the mean would have a value of 73. And 3 standard deviations above the mean would have a value of 75. We can do the same thing going the opposite direction from our center. So 1 standard deviation below the mean would have a value of 67. We'd be going down by 2. 2 standard deviations below the mean would be a value of 65. And 3 standard deviations below the mean would be a value of 63. So that's sort of a picture of what the distribution would look like with the mean and the standard deviation. So next thing we want to think about is Bob's z-score. So his z-score was negative 0.5. So one thing to keep in mind, if you have a negative z-score, that's telling you the value is below the mean or smaller than the mean. If we have a positive z-score, that means just the opposite. The value is above the mean. So that's one conclusion we can draw right away, is that Bob's height, since it has a negative z-score, is going to be less than the mean. We know the mean is 69 inches. So that tells us Bob's height has to be less than 69 inches. So we're looking for which of the following statements is true. A, Bob is shorter than 69 inches tall. We just discussed that exact thing and we decided that that's valid, that's true. So I'm not going to eliminate A. B, Bob's height is half of a standard deviation below the mean. So we know because his z-score is negative that it is below the mean. The other claim it's making is that it's half a standard deviation below the mean. And that's what this value is telling us, 0.5. That's equivalent to 1/2. So a z-score of negative 0.5 would be the same as a z-score of negative 1/2, which would be telling us that value is half of a standard deviation below the mean. So B is also correct. Bob's height is half a standard deviation below the mean. C, Bob is 68 inches tall. So in the problem, they did not tell us what Bob's height was. But let's see if we can figure out what it is based on the information we're given. So we know for sure it's going to be less than 69 inches. That was our mean. We also know that it's half of a standard deviation below the mean. So let's think about what our standard deviations were. So it said the standard deviation, or the average distance of the value from the mean, is 2 inches. So here we're looking at just half of a standard deviation. So if one full standard deviation is 2 inches, half of 2 inches would be 1 inch. So half of a standard deviation would be equivalent to 1 inch. So we now know that Bob's height is 1 inch below 69 inches, which would be 68. So C is also true. Bob is 68 inches tall. So here the correct answer is D, all of the above. Last question, 23. So it says at a large high school, a student took a series of advanced tests. Each test covered a different subject area and had a different number of questions. Also, each test had a different mean and standard deviation from the other tests. So the mean score on, let's say, the science test is not the same mean that would be for the math test or the civics test. They all have different means, different centers, and different standard deviations, different amounts of spread. Marquita is one of the students who took the test. She wants to see on which test she performed best. So we know she took a series of tests. So she's trying to figure out which one did she do best on. So which subject area maybe did she perform the best in? And the question they're asking us is, which of the following methods should she use in order to see on which test she performed the best? So A says compare her total scores on each test. So is that one way she could see on which test she performed the best? That might not necessarily be the case. All the tests had a different amount of questions. Maybe the questions were all worth different amounts of points. So maybe the science test had 10 questions. They're each worth 1 point. Maybe the math section had 33 questions, and each question was worth 3 points. So if all I'm looking at as the total score, that's not going to be a good indicator of on which test she performed best, because they all have different amounts of questions and different questions are worth different points. So we'd be comparing apples to oranges. So we'll eliminate A. B, compare her percent correct on each test. So that's a little better. We're moving in the right direction. We're not looking at just the total score, but what her actual percentage was. Did she get 98%? Did she get 80%? So at face value, you might be thinking someone who scored 95% on a test, we'll say it was the science test, and maybe she scored 80% on the math test. If we were comparing these two, we would think 95 is a higher percentage than 80. Therefore, if I was seeing how well I did on all the different tests, I would just need to find the higher percentage. That seems reasonable, but there are a couple problems with that. One problem could be maybe the tests have different levels of difficulty. So what if the math questions were much more difficult than the science questions? So if I knew that all the questions on the math test were going to be much more difficult, much more advanced than the questions that were on the science test, I might interpret the difference in these percentages differently. So maybe the reason I got a lower percent on the math was just because it was much more difficult, and overall I did best on the math test. So just from the percent correct alone, that's also not going to give us a real accurate comparison. Still comparing apples to oranges here. C, compare her z-scores on each test. So that could be an option. We'd want to know what a z-score is to help make that determination. So a z-score is something that tells us how far above or below the mean a particular value is, regardless of, say, different populations. In this case, different tests. So overall, z-score is telling us, regardless of how you're measuring something, how far above or below the mean you are. So if Marquita had a z-score of -1, that would tell us that she was 1 standard deviation below the mean. Answer choice D says compare the number she missed on each test. So that's sort of similar to maybe A. Just comparing how many questions you missed on each test isn't necessarily a reliable measure of which test you did the best on. especially because we know there's a different number of questions on each test. So we can eliminate D, and the correct answer choice would be C. Compare her z-scores on each test. So, for example, let's say on her science test, her z-score was -2. On her math test, her z-score was +2. So, z-scores are directly comparable. So we know for the different tests, science and math, they have different numbers of questions, different difficulty levels, different means. But once I change the values or the scores to z-scores, that allows us to compare apples to apples instead of apples to oranges. And that is the main point of a z-score, is to be able to compare things that are measured differently in a meaningful way. Here, a z-score of -2, that means that she performed 2 standard deviations below the mean. So she maybe didn't do as well on science. She's below the mean by 2 standard deviations. In math, her z-score was +2. Positive means above the mean, and she's above the mean by a full 2 standard deviations, which is a lot. So she is definitely better at math than she is at science. Sort of a real world example to think about to help you get a better feel for the z-scores. So tens of thousands of students apply to colleges every year. We could say we're talking about the University of Washington. You can only accept so many students. Let's say you've accepted just about everybody you could. You're almost full, but you have space for one more student. You're left with 2 different students, each with similar backgrounds, extracurricular activities, GPAs. One thing that's different is, let's say that one of the students is using SAT scores. So that's, in most cases, the first 2 things college admissions look at is what are your test scores or SAT scores, what was your GPA. However, in the state of Washington, you're not required to take or use your SAT score. You have another option, which is called the ACT. So we might be down to 2 students. One of them took the SATs, I know there's a total of 1,600 points. ACTs, I'm not sure how many total points there are. I think some of the subject areas might be slightly different. So if one student only has an SAT score and the other student only has an ACT score, how can you equitably and meaningfully compare those two values? And that's where the z-score would come in. So that is the solution to the problem, is to convert both the SAT and ACT score into a z-score. And then we just have to see which z-score is larger, and that would be the higher scoring student. So z-scores, again, really important, help us compare apples to apples. Because if we're looking at apples to oranges, you really can't make any comparisons or draw any conclusions about the meaning of those values.